Hi, everyone. Welcome to the second talk. And we have Julio from Bazel team talking about dynamic execution.
All right. Hello, everyone. So, I've been in the Bazel team for, I think, about 4 years now, focusing on especially like local execution aspects of Bazel. You may have heard my name from the sandboxing stuff, especially on macOS. In our team, we support specifically macOS builds and iOS builds at Google. So we've been doing a lot of work to make those faster. That has been the primary focus of our work. And today, I want to focus on this feature that we have called dynamic execution or dynamic scheduling, which is supposed to give you the best possible clean builds and incremental builds, both at the same time. So in this presentation, the main goal is to basically walk you through what this feature is. It's not very complicated conceptually, but we'll get over that. And then I'll dive into details of how it works and how it doesn't work, or it didn't work before. We've had a lot of problems with it when, sorry, this was written by someone else a couple of years ago, Philip from our team, and we've had to do quite a few of changes to make it work better. With that said, let's recap a little bit how Bazel works. This is obvious to many of you probably, but so as you know, we have a bunch of data sources that live on your file system probably, like the red boxes are what I'm talking about. And from there, we build this in-memory graph, which are the green boxes. And we have some targets in memory, we have configured targets, we have a bunch of actions that we have to run. So today, we're going to focus on specifically the action execution part, right? We have all these actions that we have constructed, which essentially are like command invocations, compilers, linkers, whatever it is that you have in your build. We have to run those things, and we want to do it fast. Diving into this, so we've loaded this into memory, and then we have the execution phase. So we have basically two kinds, and we can run it in different ways. In a clean build, basically, you have to build everything from scratch, right? You have started with a clean project, if you did a git checkout or whatever it is, and Bazel hasn't started yet, so you have no state on what's happening. So you do Bazel build, ... or whatever it is, and then you construct the build graph in memory, which are all the green boxes that you can see here, and essentially you have to go over the whole graph to compile and link your final application. The parallelism of this process is determined by the -- jobs flag, more or less. We'll get into that later. And essentially here we have two CPUs on your machine, and that means you can only run two things at once. Just as we do this locally, we can also do it, obviously, remotely, right? If you have enabled remote execution, which thankfully there were a couple of talks this morning that covered a lot of the stuff that I was going to say, but I'm not going to say, then you can take advantage of many more CPUs or workers to run your build faster, right? You have all these different workers. Now we have 5 workers. We can run all the actions in parallel. So essentially, you can get the best possible clean build time. And here again, we have the job setting, which you would have to increase to take advantage of this parallelism. All right, this is for clean builds. So then we have the same, but for incremental builds, right? An incremental build, for this talk, we will look at those that are, you touch mostly leaves. You touch the leaf of your project, and that has to traverse the graph, mostly just in one path, and has to rebuild things in between. So in this case, we touch 1.c, which is a source file that had no other dependencies, and that kind of invalidated the library it belongs to, that has to be relinked, and the final binary that has to be relinked as well. In this case, all the white boxes don't have to be reevaluated because you didn't touch anything in them. And in this case, even if we have 2 CPUs, we can only use one of them because we're limited by the change that we made. So that's for local build. And in this case, local build probably gives you a pretty good build time because you just need a subset of the resources that you have. So what that means is if you enable remote execution, you still have all those workers that you had before, but you are only using one of them, essentially. Easy. And again, in this case, the job setting would be a limiting factor if you had a lot of invalidations in your graph, but in this case, it's just, you're using only one executor. So we've been seeing we can run things both locally and remotely, and the way you do that is you can configure it via flags, right? So you could be even fancier, as George from Uber was explaining this morning. and say, well, I know that compiling 1.c works very well remotely, so I'm going to say, for this specific action, I always want it to go to the remote worker. But for everything else, or maybe b.c, I know that's very costly to be sent remotely, maybe because it has too many inputs or something. So I want that to always happen locally. And you can use flags and say, well, Bazel, do it this way. Using flags has some problems. First, it's a pain, right? I'm sure you're all tired of passing flags to Bazel. And the other problem is that you have to know upfront how the actions behave, right? You need to know exactly that this specific action or this specific type of actions will behave better locally or remotely. And if things change in your project that change those constraints, you need to change the flags. You need to remember to do that, and it's hard to evaluate, and it's hard to decide how to do that. The other problem is, for example, if we force b.c to run locally but via this flag, then even if that action happened to be cached or available in the remote cache, you wouldn't be able to use it, because you would never consult the remote cache to check if that action was there. So the solution essentially is to use this dynamic execution thing that we've been talking about, which is basically for every action that you have to run, you send it to the remote executor, and you also run it locally. And then you just pick whatever finishes faster and discard the other one. An important thing here is that because you're going to run the same action in two places, the tool chains and the environments have to match. Otherwise, the outputs will be different, and that would be very problematic. It's a big assumption, but if you're using remote execution, you really need to get these things right, and it's tricky. But assuming that you can do that, then this model works pretty well. So with this, as I was saying before, let's say b.c, it's always faster locally, but for whatever reason somebody happened to build that remotely earlier, and it was cached, then you would take advantage of that immediately without having to rebuild it in your local machine, even if you thought that building it locally would be faster. So that's essentially dynamic execution in concept. Very simple, right? So now we will dive into the details a little bit more. But first of all, how do we configure all these things today? Like I was saying, you can pass some flags and to say I want this to run remotely, this to run locally. So that's all done via something we call strategies, which is Bazel's abstraction around the exec system call, as George also mentioned this morning. So essentially, when we want to run any subprocess from within Bazel, we use a strategy, which is a abstraction to say, okay, run this thing, and then when you have the result, give it back to me. You can change strategies at any time. They do not invalidate your build graph, because essentially they just configure the behavior of this function, of this execution, but they do not change the semantics of the output, right? They should be the same outputs, no matter what strategy you select. So with that in mind, I'll cover the major strategies that we have today, so we can later see how they play with the dynamic scheduler. The most obvious strategy that we have is called standalone or local, which essentially just runs your process in the output tree, just where it should be, with the paths to the output files where they are in the final locations, and that's it. Spawn is the word we use in the code to represent the subprocess, but it's essentially the same thing, right? Easy. You call standalone exec, you run this command, it runs it somewhere in your output tree, and you're done. That is fine, but then in Bazel, we say that we are correct, right? So we had to introduce some boxed execution to make sure that these commands do not affect, do not pick like unexpected dependencies or don't have side effects in your system. So then you have the sandboxed strategy. This is a bit more complex, right? We have to first, for every action that we have to run or for every command, we have to create a sandbox first, which involves possibly copying files or creating a ton of symlinks, blah, 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 prepare the environment. Then we execute the spawn inside that sandbox. When we are done, because this sandbox is a separate directory, right, the outputs were not written where they were supposed to be. They are written in a sandbox. So we need to move them in place. And when that's done, we can finally destroy the sandbox and call the day, right? We can say that's done. This is costly. I mean, creating a sandbox, and we'll see later, creating and destroying is costly. The fact of running a process inside the sandbox itself is also a bit costly. Not so much, but it is a little bit. But we'll get to that later. And the other strategy that we have to consider in this talk is the remote strategy. very simplified. We want to run something remotely, right? We send it to a remote execution worker, and then the service comes back to us saying, hey, yeah, I can run this, but I'm missing these input files. Please send them back to me. So you send up files that you needed for the action. You try again until you're done, and then you finally, when the remote execution succeeds or gets a cache hit, you download the outputs, and then that's it. We're not going to cover the worker strategy, but that's the other important strategy that we have in Bazel, I would say. So with that in mind, the dynamic scheduler, and we call it scheduler in many places, but that's a very strong word for what it does. It's actually the dynamic thingy, scheduler is just one more strategy, right? The dynamic scheduler just wraps this exact call, and the dynamic strategy is different than the other ones because it's actually wrapping two other different strategies, one that does things remotely and one that does things locally. By default, that would be the remote execution and the sandboxed strategy. So, you have a number of jobs coming in to dynamic execution. That's your parallelism that you have defined in your command line, essentially, which for RB, I heard this morning was something like, what, a few hundred, I don't know. But, yeah. For a remote service, you need to provide several hundred, probably, to get good performance. And then the dynamic scheduler will kind of fork and run the same thing twice, and then it will pick the fastest result in some way that we will see soon. Now, as you can imagine, there is a problem here, right? If you use the number of jobs for the parallelism for the remote execution, and you try to do the same for local execution, you will kill your machine. As I said, we have 300 remote jobs, and you try to run 300 processes locally, your laptop, for example, will not tolerate it. So we have to add one more thing, which Bazel already had, which is this concept of local resources, right? In Bazel, every rule and every action pretty much define how many CPUs and how much RAM they need to run. It's a very bad model or approximate model, but it more or less works. And so Bazel has a tracker so that every time it wants to run something locally, it will say, do I have enough spare resources for what you're asking me? And then it just counts that, tracks that, and that's how we control, we have a subset. Sorry, we have N jobs running remotely, but then of those, we will only have a small subset running locally, which are essentially bound by the number of CPUs. And when the local execution starts finishing or they are stopped, then you free those resources, and then you can run more of the remote actions locally if you have to do that. Okay, so conceptually, that's pretty much everything that there is to know. How does this work in practice? And for that example, I'll focus on the use case we've been working on, which are essentially iOS builds at Google. And those have traditionally been local only. For a long time, they didn't have access to remote execution for various reasons. But essentially, like the Macs that we have at work, we couldn't reach like our production services from Macs, and we didn't really have Blaze. Well, porting Blaze to the Mac was a big project, and until that was completely done, we couldn't use the remote execution service that we have in Google. So people that had to do iOS builds from their Macs were forced to use local builds only. As you can see from the numbers, those are some numbers I got from one of our large iOS builds, iOS projects, sorry. You can see that incremental build times, and those were computed by touching just one of the leaf source files that I was showing you earlier in the introduction, are pretty good. I mean, 17, 20 seconds are not great, but they are not terrible either. The clean build times are just awful, right? You have to wait almost an hour to build your app on your laptop and 20 minutes on a very powerful machine. That's not great. So a lot of our work was to actually provide remote execution for these iOS builds, and we spent a long time doing that. Right? Then we added this feature. We were so happy. Let's try what happens. Let's try to see what happens. Not great. We spent a lot of time doing this, clean build times, massively improved, but incremental builds are now very bad. Specifically, This is what we were listening to this morning. Some actions are not designed to be run remotely, right? Or they are very bad for various reasons. In particular, in our system specifically, linking was very bad. A few years ago, just like running a linking operation that would take 40 seconds on your machine, it would maybe take like 8, 10 minutes remotely. So that's where you see there, right? Those numbers increasing significantly. We could fix that, and we have actually fixed it. We made remote linking much better. But still, you can't beat local linking, for example, when all the files are already there. Right? Having to send anything remotely will already kill your performance. So the idea of the dynamic execution is to solve this. And if you can take advantage of both remote and local resources at the same time, you essentially get, for each row, you can see that we got the best of both worlds, right? For clean builds, we get the remote behavior, more or less. And for incremental builds, we get exactly the local behavior. There's some overhead in some cases, but well, you don't see it here, but it exists. We will see later. But yeah, we can get the best of both worlds, essentially. Okay. So the idea that you have to remember, if you forgot everything else I said, is that remote execution is great, but by itself, if you don't do anything else, you may not get all the advantage that you might think you might get out of your builds. This leaves aside making sure your build graph is nice. You don't have gigantic actions and everything like this. But if your build graph is not friendly to parallelization, nothing like this will help you. So first, fix your build graph, and second, use remote and local resources at the same time. Okay. Now, why is the dynamic scheduler problematic, or was problematic for us? It all comes down to its history, right? On the left side, we have the builds that we have had at Google for a long time, right? They have always been, for the most part, remote, and they have been run from very powerful workstations. And the goal of the dynamic scheduler, when it was introduced, and it was introduced in this context, was to make incremental build times faster, specifically for languages that benefit from persistent workers. And I think examples were like Dart and TypeScript, where you really can benefit from those workers being there. You don't have to send anything to the remote execution, and you get super fast behavior there. Now, the problem is for our iOS builds, and actually for any build outside of Google, all the open source builds and all builds that you might have, they are probably different, right? They have been traditionally local only. You might be running them from machines that are not as powerful as a workstation. And the goal there is to make sure that clean build times are better by using like remote execution, as we were seeing. So the problem is here, again, that the dynamic scheduler was written for the first use case, and there were some implications in the code that prevented it from working properly in the second use case. And I want to dive into some of them now. We'll cover 3 different problems that have time, their solutions, and what our goal is essentially for this. And then we'll be done. Okay, the first problem is output locking, right? We have the dynamic scheduler running 2 things at once, and these 2 things want to write to the same output files, right, in your output tree. How do you fix that? Well, you put a lock. Very, very simple. Actually, the way this works is in the code, we spawn the 2 strategies, remote and local, or sandbox in this case. They do their stuff, and then right before they have the outputs available, they take the lock for that specific action. And in the remote case, we fetch the outputs and put them into their location. And in the sandboxing place, we move the outputs to where they belong. That sounds great, but as you may have heard me say in many other places, sandboxing is slow, especially on Mac. I took these numbers from a previous blog post that we had in the Bazel blog. And you can see the red boxes are essentially what kills performance in the sandbox, at least for macOS. Creating the sandbox is very slow. Moving the outputs should actually have been green, but whatever. And destroy the sandbox is actually more costly than creating the sandbox itself. And you can see here, for Bazel, the penalty of having a sandbox is not great, but it's not terrible. But for the iOS apps, it's awful. And the problem there is that our actions have tons of inputs, which means you have to create tons of symlinks when you create the sandbox, and that doesn't work very well. as a side note, I've been trying to fix this with the SandboxFS implementation, but it's still not as good as I think it can be. But it's a side note, it's a side project, so I don't have much time for it, so it will get done someday. Okay, so if sandboxing is low, what do we do, right? In our case, we disable sandboxing for interactive builds because they are too slow. We still have them enabled in CI, you know, and everything that gets checked in will be sandbox safe, but for local incremental builds, we don't have that. So then we need to make the dynamic scheduler work well without sandboxing. And so this is what happens, right? We have now the local strategy, but the problem is, if you're going to run a compiler or something inside the output tree, you don't know when that binary or that processor is going to actually touch output files. So therefore, you must log the output upfront. Right? Before you start anything, in the previous cases, we did the execution before taking the log, but for local execution, we take the log before we do anything, which, you know, it works. If you do it this way, it works fine. You can imagine that you are prioritizing local execution more than remote execution because you will take the log much sooner than otherwise, but it works. Now the problem is we roll this out to some teams and we got this, right? These are median build times measured from the user's laptops for one specific iOS app. And blue is the locally only build times, and red are the dynamic build times. Based on what I have explained until now, you would expect dynamic builds to always be better than local builds, right? Because you are doing the same thing as you're doing locally, plus you have access to remote resources. But as you can see, the line jumps all over the place, and it makes no sense. Not good. Needless to say, we measured this with micro benchmarks, and everything was great. But when we started looking at actual user behavior is when we see that things weren't playing out as we thought. So then we had to go back and see what's happening. Okay, so one of the problems is there, right? The remote path is taking the lock before downloading anything. So at that point, you have taken a lock. You have no idea how your network is behaving, but now you cannot go back. At this point, you have started downloading your outputs, and that may be slow, or it may break. And if the connection breaks for whatever reason, your build gets stuck, and you have to Control-C and start it again. So how do we fix this? Well, you can imagine it's not very complicated in theory, but in practice was a pain. We download the outputs before we take the lock, right? We put them aside in a separate directory, and then once we have them all ready, we take the lock and we put them in place. This is, again, very simple, but when we did this, there were fun problems because in the previous model, when the dynamic scheduler decides to stop the remote path, it would always do it before the red box, right? So it would always cancel the remote execution. It would never cancel the downloads. But now that we moved the downloads before, we are issuing cancellations on a code path that was never designed to take them very well. So we started seeing like memory leaks and things that didn't cancel properly, and they would run in the background, and JVM would crash. Not great, but eventually we fixed it. I know Jacob did the same change for the RB module, so you have these in both the internal and the external versions, and that works. We tried that. We rolled it out like a month ago, as you can see in the dates, and so far, the red line has stayed below the blue line. Hopefully, it will stay that way forever, but I'm not super convinced yet. Okay. So that worked, but doing this introduced a different problem, which is now the remote path takes much longer than it did before, right? Especially if you get a cache hit. If you get a cache hit, remote exec will return immediately, and then you're ready to take the lock, but the local path might have already taken the lock, and then even if the remote service comes back and says, hey, I have a cache hit, you can't use it, right? You're now waiting for your local execution to finish, when maybe downloading the thing remotely would take only, it would be a small output file. So how do we fix this? The problem here was essentially that we were using kind of a cooperative locking mechanism, right? We expect every code path to wait and take a lock and then decide what to do. But no, we have to change this to become kind of preemptive, right? We want the local execution to start anytime, whenever it's ready to have, whenever there are local resources, we let the local execution start. And then, whenever the remote code path is ready, we want it to explicitly cancel the local execution, wait until everything is clean, make sure there are no files in place, and then we're ready to move the outputs. This has been very problematic. I mean, there are two flags to enable this behavior. The first one, we had to rewrite the dynamic spawn strategy completely to implement this kind of cross-cancellation feature. And when it works. I think there is still a small race condition somewhere, but I'm not sure if it's by this feature or this feature exposed it. But with that in place, you can enable the other feature, which removes the lock from the local path. And then you can take advantage of this model. Now, we still have to tune. It's not the default yet because we haven't tuned performance. But when we do, it should be possible to make it the default. OK. So I mark wait for cleanup there in red because that has also been problematic. Something that seems very simple turned out not to be so much. And the reason is because canceling local processes is complicated. So as an example, we have here, I tried to paint like what's happening inside in Bazel. We have the dynamic strategy that starts doing an exec towards the local path, right? And the local strategy will then have to run a process. And the way you run a process, well, you run fork and exec, and you have the thing running, your compiler, and at some point, the remote execution will have finished, and we'll say, well, I want to cancel the local strategy now because the remote path is faster. So then the local strategy sends a kill signal to the child process. You wait for the process to go away with wait PID, which we were not doing before, so I had to fix that. And then we return. Now, the problem is if you don't wait, sending signals is not synchronous, right? Sending a signal to a process, the process will react to it at some point, but not immediately. So if you don't wait for it, there is a race condition between the process maybe writing some more files before actually you, and then you may get a conflict in the remote execution when you try to write to the same files. Easy. But now what happens if that child process decides to be nasty and starts another process, right? Well, you send the signal to the process dies, the grandchild process continues running, gets reparented to init, and you've lost control of it. And now we are in trouble. As it turns out, there are many tools that do this because there are many wrapper tools, shell scripts that wrap other tools. And when you have a shell script that does that, then you hit this problem. So how do we fix it? It's not difficult in theory. You can use a process group, right? We have between the fork and exec of the original design, you do set process group ID for the child process, right? You create a new process group. And then when you have done that, you are able to send the signal to the whole group. And then all the processes die, but you can only wait for one of them, right? Wait PID will only wait for one of them. There is still the problem of what happens with the other child processes that have been leaked. They are dead, probably. Most likely they are dead because it's a kill signal, so even if it's not synchronous, they will die very quickly. But there is still a chance of a small race condition. So I've been trying to fix that. I actually fixed it last week, but the change had to be rolled back, so I will try again. But basically, we have to wait until the processes are really gone. And the way to do that varies across platforms. I kind of wrote about it in that link at the bottom. So in Linux, we can use the child subreaper feature, and on macOS, we have to walk the process table to make sure that everything is clean before we can actually return control to Bazel. Great. But Java, you cannot do these things from Java. Right? Java doesn't give you access to process groups or wait PID or all these things. So instead, Bazel has this binary, and this has been there forever. It's not a new thing with the dynamic scheduler. It has been there for a long time to control tests, but now I have this process in between, which ships with the Bazel binary, and it's a trusted process, right? We know that it behaves well, so we can exec it, and then we can send it a seek term to kill it instead of a seek kill, and then we can rely on the process wrapper of doing the cleanup by itself. The process wrapper is in C++, or well, C with some C++. And then, yeah, Bazel can trust that that thing is like a unit, and we just take advantage of that. Again, as I said, this was added for for testing, I think, to make sure the test didn't leave like sub-processes behind. But for us now, this is very useful, and it was good that it was in place. Otherwise, we couldn't have done this properly. And we have had to modify it to the waiting until all PIDs are gone. You can read more in that Bazel bug and in that other blog post in my personal page. And finally, the last problem I want to talk about are tree artifacts. Another difficulty that showed up. So tree artifacts is a name for essentially actions that, so typically most of your actions will create output files, right? But some actions will create directories. And you don't know what's inside the directory, right? You just know that this action, like I run this, specifically Apple tools like to do that a lot. Like I run this thing of my source files, and then I get this output directory with many many output files inside, whose names I can't predict easily. So then we have this concept of tree artifact, which encapsulates this. That here, well, we have the two cases, right? We have remote execution, standalone execution, not sandbox anymore. We are looking at standalone because that's where the problem lies. If it's sandbox, we wouldn't have this problem. These strategies start your process. Your process will create some output files in a directory. And then for the remote case, we fetch all of them and we put them in their place. And for the local case, we just wait until the process is done, and that's it. Just for clarity, in this page and the following, yellow is your sub-process, and green is all Bazel code. So you have to do that. But what happens if your tool is creating more files than it should, right? You have, and we have seen this, of course, otherwise I wouldn't be talking about it. You have a wrapper tool that invokes some other thing, and as part of the process, you create a ton of temporary files in your output directory. You create the real output files, and then right before you exit, you delete the temporary files so that the output tree artifact only contains the things you care about. Same thing in both cases. Okay, now you have to stop these things from running at some point, and you're so unlucky that the cancellation happens there for the remote case, right? You have created temporary files, you have created output files, now you stop running. That's fine. You didn't fetch anything to your drive, so you never saw the temporary files. They never made it to your disk. Everything is happy. Bazel will take the output of the other path, scan the list of files in the directory, and treat those as your output, really. But if that happens to happen in the standalone case, we're in trouble, right? We have canceled. Remember that the standalone execution is running now without taking the lock, because we have this feature to remove the lock. So you have a process running in your output tree. It creates temporary files. It creates output files, and then we stop it. There is nothing there to clean up the temporary files. So now remote execution wins. We fetch all the outputs, and then Bazel looks at the list of outputs that it fetched, the list of files on disk. It finds that they are different, and it freaks out. And then your build fails, or I think Blaze even crashes or something. Not good. So I mean, we've played with different solutions, but the easiest solution here was to change the standalone strategy to when it's canceled and waits for the process. After waiting for the process, it goes and deletes any tree artifacts that are on disk, cleans them up. And so when the remote execution path downloads things, it's a clean directory, and there will be no side effects. And when I was saying that there are some bugs still in the localized execution thing, they are still here, I think. And I'm not sure why, but that's, in some cases, this still fails. All right. And with that, that's all I wanted to say. Just to remember, dynamic execution, I think it's a must for good performance if you use remote execution. If you want to play with the new features, you have those two flags I mentioned. And I'm actually writing this down in a set of blog posts that I don't know if I'll publish in the Bazel blog or in my own blog, but they will be like a summary of everything I explained here, and probably cover some more detail. And with that, that's it. Thank you. Questions?
Yeah, a couple questions.
For the standalone execution, have you considered like a partial sandbox where the output stuff is carved off into different directories so that you can cleanly rename it, but all the inputs are left where they normally are?
So the question is, for the standalone,
Point where you try to make it so that only the output directories are pushed somewhere else.
so the question is, if for standalone execution where we don't take the log, if we could somehow put the output somewhere else so that we don't have to, so we can actually move them and not have the interference.
Full sandbox.
Maybe. The first, I thought about it a little bit, not much, but the first thought was maybe I could change the command lines to point somewhere else, but then what happens with cache hits, it's a bit complicated. The second problem is like, I have to find a portable solution that works on Mac and Linux, and then, yes. For Linux, I'm sure you can do it easily, but for Mac, you can't. So then I wasn't. I'm sure there are other ways to do it, but this seemed like the most reasonable. Okay, the comment is that in Windows, you can do it, as we heard this morning. Great, but we don't. I do care, but I haven't had a chance to have time. One more question.
Given that there's fewer CPUs locally than there are remotely, how does Bazel prioritize what to run locally first?
Okay, the question is, there are fewer CPUs locally than remotely. How do we prioritize what to run first locally? Aha, that's why I said that the scheduler word is very strong. There is no scheduling here. Bazel just, I think there are some heuristics in Skyframe to decide what actions to run based on the number of jobs. But from there on, it's just a competition on who gets the resources first locally. I would like to make that better, but we haven't had the chance yet. And I don't have any idea specifically in what we would do.
Thanks.
Anything else?
Is there a plan to use some kind of historical performance graph to decide whether remote versus local and kind of balance your execution so you get more efficient in your performance?
The question is if we have thought about looking at historical data to decide whether to run something locally or remotely. At some point, this came up. I think someone that knows this system very well said that you can't do that real time because checking anything remotely will kill your performance. I haven't looked at it more. One idea that came up was, well, Bazel has this persistent server that's running all the time in the background. So maybe in between commands, you could fetch historical data or prepare your own to decide things later, but.
Fetch the historical data at runtime, but you can now refresh historical data to look at another kind of cache to run.
Right, we could prefetch it, yeah.
Maybe you have enough servers, but if you have less number of servers, maybe it's more efficient. You don't have to everything both sides.
Maybe. It's something else to invest. It's kind of along those lines. Like, how do we decide what to run locally versus what not? Looking at historical data would be an option, but we haven't thought about it yet much, no.
You're out of time, sorry.
You can talk about it later.
All right. Thank you very much, Julio.